In this video, I'm going to use synthetic division and other factoring techniques to find all roots of a polynomial. Now, in this first case, we have a function that is a polynomial. It's x cubed plus 12x squared plus 45x plus 50. And we are also told that x plus 2 is a factor of this polynomial. So that means when I divide it, I should have a remainder of 0. So let's go ahead and check that out. Let's build our synthetic division with 1, 12, 45, and 50 as our coefficients. The synthetic division would use a -2 on the outside. And remember, we're using a -2 because this says x plus 2. X plus 2 is the factor, and we are checking the root at x equals -2, because when x is -2, that's going to set this factor equal to 0. That's where our root is. So the synthetic division would go like this. I bring the 1 down, multiply the -2 times 1, add these two together. 12 and -2 adds to a 10. 10 times -2 is -20, and 45 minus 20 in this case is 25. -2 times 25 is -50, and we have a remainder of 0, which is what we expected. Now, what I want you to recognize here is that this really tells us a couple things about the polynomial. The original polynomial was x cubed plus 12x squared plus 45x plus 50. And what we now know is that when we factor out an x plus 2 evenly from the problem, what we're left with is this 1x squared plus 10x plus 25. So really I have the product of these two polynomials, x plus 2 times x squared plus 10x plus 25. That's where this came from. And we could then try to factor this remaining trinomial. And fortunately for us, this factors very easily. If you think back to the work that we did in Unit 3 about factoring quadratics, you should recognize that we can find two numbers that multiply to equal 25 but add to equal 10x. So those two numbers are 5 and 5. And fortunately, since we have this completely factored now, we learned from the last set of notes yesterday that each of these factored binomials represent a 0 for us. And so I'm going to show this one more way before I list the zeros. Since we have two of these x plus 5 factors, I can write that as x plus 5 squared. And this leads us to recognize that there are roots at x equals -2, just like we knew from before. But we also have two roots because of this power here, but two roots at x equals -5. And we're done with this problem. We started with a polynomial, and we found all roots of the polynomial. Let's look at another example. We have another polynomial here that can be set up with synthetic division, and we know that x minus 5 is a factor. So I'll use the coefficient 1, -6, -7, and 60, along with a +5 in the front, and complete the synthetic division. So with our synthetic division, we've shown our original polynomial to be equal to the product of our known factor and the result after the synthetic division. These two pieces go together here. Now let's see if we can factor this trinomial again. And I think we can. We can find two numbers that multiply together to equal -12, but add or subtract to equal -1. And for that, we can use the numbers 4 and 3. And I think we should use a -4 and a +3. And again, it's really nice once we have this original polynomial written in what we call factored form, because each of these factors represent zeros of the polynomial. Zeros or roots. They mean the same thing. So the zeros or roots of this polynomial occur at x equals 5, x equals 4, and x equals -3. And we are finished with this problem. Let's try one more. We have yet another polynomial and a known factor. So we can use synthetic division to divide this one as well. Now would be a good time to actually pause the video and try this one on your own and see if your solution matches up with mine. Resume video playback in just a few moments to check your work. And here you have it. The synthetic division, when complete, leaves us with x squared plus 6x plus 5. And that trinomial can be factored again into x plus 5 and x plus 1. So with our original factor, along with the two factors that came from this trinomial, we see that our roots, or zeros, occur at x equals -3, x equals -5, and x equals -1. When we combine the knowledge of our roots with our knowledge of graph behavior that we reviewed yesterday, this gives us a pretty good idea of what the graph should look like without going to a graphing calculator. Notice we did all of this work today without the use of a calculator, and we can continue to sketch a graph of this equation without the calculator as well. In this case, I know that x will produce a root at -3, so I've labeled these tick marks to represent one space. So here's -1, 2, 3. There's another 0 at -5. That'll have to be here if I extend this x-axis just a little bit. And then we have a 0 at -1 as well. Since our original equation had a positive leading coefficient and an odd degree, I know the tails of this equation, the tails of this polynomial's graph should be pointing up and to the right, down and to the left. And if the graph has to cross the x-axis in each of these three spots, I know the dimensioning in between the tails might look something like this. So even though the problem didn't ask us to predict what the graph would look like, I think that's something that we should start considering now while we're working on these problems. Please be sure to bring any questions to me when we see each other next, and I'll try to address them. We'll cover more topics in the next video.